So to begin with, we're going to use the quadratic formula to solve for the first problem. Again, to save time in the video, I may stop the video, put some information on the screen, and then continue the video. So if you see all of a sudden a bunch of work done, it's because I'm trying to save time on the video, and some of these things are with you, some of them are not. So to find the x-intercepts using the quadratic formula, we use this formula here. The a value is 1, b is 4, and c is 5. The opposite of b is -4, because b is 4, plus or minus the square root of 4 squared minus 4 times the a value, which is 1, times the c value, which is 5, all over 2 times the a value, which is 1. Go ahead, if you've not simplified this, go ahead and simplify this, turn the video back on when you're finished. So completing the problem underneath the radical, simplifying that, we get the answer of -4, and then the denominator is 2. In this problem here, we have no real solutions. As we've talked about, anytime you have a radical that is a negative number, we can't take the square root of a negative number. So at this point, there are no x-intercepts. So the question is, let's investigate why there are no x-intercepts. So in this review, so go ahead and put this equation into vertex form and then turn the video back on when you're ready. When you turn the video back on, the work will already be done because this is part of lesson 5.2. So in using our complete the square method, first thing you do is subtract 5 from both sides. Then we're going to create a square by finding the value in the top right corner. We need to split the 4x's up, put 2x to the top, 2x to the right side. So the square at the top would be a 2 by 2 square. That's the reason for adding 4 to both sides. The dimensions are an x plus 2 each side. That's the x plus 2 squared. We finish off simplifying the left side, and we end up with x plus 2 squared plus 1. So the vertex is at -2, +1. Since the a value in the problem is 1, then that means the graph is going over 1, up 1, and over 1, up 1, because a value is how much the graph is going up from the vertex when you go over 1. So that means this graph, a is positive, is going up. So the question is, why are there no x-intercepts? Is because the graph itself begins at -2, 1, and the graph, because a is +1, goes up, so therefore it will never intersect the x-axis. So when using the quadratic formula, if you get a discriminant that's negative, that's the b squared minus 4ac in the quadratic formula. If the discriminant is negative, that's telling you that the parabola will never touch the x-axis, so therefore there are no real solutions. So mathematics, we have lots of mathematicians who've tried to solve math problems for many years. And so they developed new math systems, number systems, to address those issues. So for example, Pythagorean theorem, which was developed by Pythagoras and his mathematicians, was a fix for right triangle problems in which the hypotenuse could not easily be found because there was no number system to represent those lengths using square roots. So he is credited for developing that number system. Euler, this is the gentleman's name here, E-U-L-E-R, so Euler kind of is spelled like O-I-L-E-R, like in the football team, the Houston Oilers. So Euler was the person who's credited for coming up with a fix for square roots that have a negative number underneath them. And so he developed was a number system called imaginary numbers. So anytime you have a negative number underneath the square root, we're going to rewrite the problem so that we pull apart the number in two factors, one being the -1 and the second factor being the other number. And then we're going to simplify this problem as the square root of negative 1, which is I, and then the square root of the number, the positive number. And sometimes it will simplify really nice, sometimes it does not. In this case here, the square root of 9 is 3. The square root of negative 1 is I, so the final answer is 3I. This is called an imaginary number. I prefer putting the I after the number instead of I3. You don't want the 3 to look like an exponent or subscript, something like that. So put like when you write 3x, put 3 first, x second. We're going to treat the I kind of like an x, in that we're going to put the I after the number. In the second problem, we have negative 1 times 15. So I separate that. The square root of negative 1 times the square root of 15. We talked about today in class how to simplify these radicals. And so we're looking for perfect square factors that would work for 15. So does 15 have a factor of 4? Because the square root of 4 is 2. It's a perfect square factor. Does the next one is 9? So the square root of 9 is 3. The square root of 16 is 4. So those are the numbers we're going to be using. And so does 15 have one of those perfect square factors as a factor? And if the answer is yes, we're going to break the 16 or the 15 down further so that we can simplify that radical, because sometimes the radicals are not going to be as easy as the square root of 9, which actually is a perfect square. 9 is, which is 3. 4 is not a factor of 15. 9 is not a factor of 15. So 15 cannot be broken down any further. So the square root of negative 1 is I, and the square root of 15 just stays the square root of 15. So in this case here, it will be I square root of 15. We're going to put the radical second after the I, because again, we don't want the I to look like it's underneath the square root. So if we have like an integer value, we're going to put it first, followed by the I, and then the square root, we'll put it last. In this next problem, we have the negative 16, so we're going to break that negative 16 down into two radicals. One's going to be the negative 1, and the second one's going to be the 16. So the negative 25, again, we're going to break that down into negative 1 times 25. So we're going to break that down also into two radicals. The negative square root of negative 1, that's I. And then we look at the 16. Is it a perfect square? If it is, we can just simply replace it with this 8 number. And if it's not, we're going to see if we can simplify it. 16 is in our list. It's the third number. So square root of 16 is 4. Square root of negative 1 is I. And again, square root of 25 is 25 in our list. And it's the fourth number in our list on the left side. Therefore, 9, 16, 25. Square root of 25 is 5. So that makes the problem 4I plus 5I. Again, that number in front of the I. We treat I quite often like an x. So when if the problem was 4x plus 5x, we would add those together to make a final answer of 9x. So here we're going to take 4 i's plus 5 more i's. So altogether, the final answer will be 9. So in the next section, we're going to be using some of our algebra rules. So again, we're going to treat the I in a very similar way that we treat x. If you see, let's say 7x plus 2x, what would you do in that problem to get to the final answer? We're going to do the same thing with the imaginary I. Same thing here. If I had 4 times 3 plus 2x, how would you do that problem? All we're going to do, instead of doing the multiplying the 4 by the 2x, we're multiplying the 4 by the 2I. And same thing here. How would you add those two expressions together if the I would have been replaced with a x in both of the parentheses? So if you haven't completed these, please complete these problems and then turn the video back on when you're ready. So the first one, if I add 7x and 2x, it would be 9x. So for the second one, the problem we're actually doing, the answer is 9I. In the second problem, we could use the distributive property and multiply the 4 times the 3, which is 12, and the 4 times 2, which is 8. So that would be 8x's. So we do the same thing for the problem about an I. 4 times 3, we're going to multiply, and we're taking the 4 times the 2I. So 4 times 3 is 12, and 4 times 2 is 8I. So instead of 8 x's, it's 8 i's. The last problem, if you're going to combine like terms, you add the 3 and the 3, since it is an addition problem, that's 6. And then 2x plus negative 4x makes it a negative 2x. Same thing will be true for the second one. Since it is an addition problem, we can rearrange these. Put the terms that have just constants in them together, and the two terms that have the i's together, we could add these together. So basically, like rearranging the terms. So it would be 3 plus the 3, which is 6, and then 2 minus 4, which is negative 2, it's going to be negative 2i. So again, you're going to find that if I treat these problems like variables x instead of the i's, the rules we're going to be using are very similar. So if I is replaced in the square root of negative I, if I is replaced in the square root of negative 1, then what would be the value of I squared? Think about it, write down your answer, write down an explanation of what you think it is, and then turn the video back on when you're ready. So the example I gave in class was, we used a calculator. If I would take square root of 3, if I square it, what answer would you get? If I take the square root of 5, and if I square it, what answer do you get? If I take the square root of, let's say, 11 and square it, what answer do you get? And then finally, if I take the square root of negative 1, because I'm squaring it, again, I is the square root of negative 1, and if I square it, what answer do I get? So if you weren't sure how to answer this problem, why don't you do those problems first, think about the answers you're getting, and then turn the video back on when you're ready to continue. So the square root of 3 squared, that's 3. The square root of 5 squared is 5. The square root of negative 11 squared is 11. And the square root of negative 1 squared is negative 1. So basically the I squared problem is really the square root of negative 1. I is the square root of negative 1 being squared. So I squared is going to be negative 1. So in the next page, as we work through the problems, anytime we see an I squared, we're going to replace I squared with negative 1. So we're going to use generic rectangles here. Again, treat these problems like doing generic rectangles with x's. So it would be like 1 plus 2x and then 2 plus 3x in the first problem. What would the generic rectangle look like? And so instead of using x's, we're now using i's. Keep in mind that the problem we just did before, anytime an I squared shows up, we're going to replace the I squared with a value of negative 1. Turn the video back on when you complete the first problem, and we'll do that one together. And that'll give you some time to work on the next two, and then you turn the video back on and look at your answers. So using generic rectangle, we do 1 times 2, which is 2. And we have 2i times 2. That'd be 4i here, because 2 times 2 is 4. We're going to do 1 times 3i, the bottom right corner. 1 times 3 is 3i. And then top right, we're going to do 2i times 3i. So 2 times 3 is 6. And I times I is I squared. So the answer, because we have a pair of like terms, the answer we have is 2 plus 7i plus 6i squared. But if you recall from the previous problem, anytime an I squared shows up, we're going to replace that I squared with a negative 1. So the problem becomes 2 plus 7i minus 6. Since 6 times negative 1 is negative 6. We can simplify this one step further because the 2 and the minus 6 are like terms. 2 minus 6 is negative 4 plus 7i. So in this problem, this answer, there is a real part and there's an imaginary part. So the real part of this answer is negative 4, the imaginary part of this answer is 7 odd.